Okay, very good afternoon, my dear students. Today we can finish our second chapter by just comparing the three discussed techniques. Those are binary amplitude shift keying, binary FSK, and binary PSK. Okay, so today we can compare all the three techniques, and then we can move to, discuss some problems. We can move to third chapter. So let us go through the comparison of ASK, FSK, and PSK. Actually, in your syllabus, they mentioned like similarity of BFSK and BPSK because ASK is least preferred technique because of its main drawback that it possesses amplitude variations. Okay, so either FSK or PSK will be preferred in general. So that's why they mentioned like that. But we have to compare all the three because you have studied all the three techniques. So after this module, you should be able to learn the comparison between ASK, FSK, and PSK in all aspects. Now, all of the students, please observe the three keying techniques shown here. Please observe the first row mentions the ASK, FSK, and PSK, the three techniques which you want to compare. And first comparison is based on the factor like the definition, okay, general expression. So first you define in terms of its definition, like you know the definition for ASK. FSK and BSK. ASK is the keying technique in which the amplitude of carrier will be varied. Let us define in terms of its equation. So here amplitude of sinusoidal carrier will be varied by maintaining the okay, please wait. Now is it visible?
Yes, ma'am.
Okay, thank you, ma'am. Please let us go through the comparison of ASK, FSK, and PSK systems. So coming to the binary ASK, you know the definition. The amplitude of sinusoidal carrier will be varied by maintaining the frequency and phase of the sinusoidal carrier as constant. And amplitude is varied in accordance with 1 and 0 of the input level. Okay, so like that ASK signal, write down the general expression. Root 2 PS cos omega CT for data bit 1 and 0 for data 0. Similarly, I think you can define the FSK. The frequency of sinusoidal carrier is varied with respect to the input level by maintaining the amplitude and phase of sinusoidal carrier as constant. So that's why because it is binary transmission technique, one more point is because it is binary transmission technique, you will have two amplitude changes for ASK because binary mean that only one bit is transmitted per symbol. So n will be 1 here. So once the n value is 1, binary means that it will have two changes. If it is binary amplitude ASK, it will have two amplitude changes. If it is binary FSK, it will have two frequency changes. One is high frequency and other is low frequency. And if it is binary PSK, it will have two phase changes. One is 0 and other is 180 degrees as we specified. In binary FSK, what is the definition? AC cos 2 pi FHT for data bit 1 and AC cos 2 pi FLT for data bit 0. Okay, and in PSK, we'll have two phase changes. One is for the data bit 1, you will have same phase as carrier, and for data bit -1, you will have 180 degrees phase shift. Because in the last class itself, we discussed in M-array transmission techniques, the phase difference between any two successive symbols is 2 pi by m. Okay, so in the case of binary, m is 2. So that's why 2 pi by 2. So difference between those two is pi. See, you can consider either 0 or 180, or you can consider as pi by 2 and 3 pi by 2. Then also the difference is like pi. Okay, so at any cost you can consider, but the phase difference between the two should be 180 degrees for BPSK system. Okay, and then similarly binary ASK, what is the input general format? It is unipolar NRZ. And similarly in binary FSK also, the input signal is in the form of unipolar NRZ. Already we discussed. Okay, in BPSK, see in any kind of PSK, that may be binary or quadrature or MRA PSK. Okay, our input is should be bipolar. Okay, it should possess two levels, two voltage levels. One is +1 and other is -1. Okay, so similarly in ASK we'll have a frequency, single frequency carrier, because here frequency is constant. But in FSK, the variation parameter is frequency itself. So we'll have two frequencies. One is FH and other is FL. And in BPSK, what is the frequency? Here also the frequency is constant. So that's why it is equals to FC or omega C. Okay. Next, what about Euclidean distance? The Euclidean distance of ASK is root PSTS. Or else here TS is TB. In binary techniques, TS is equal to TB because N is 1. In MRA transmission techniques, the relationship between TS and TB is TS is equal to NTB, because a symbol is formed by grouping N bits. So that's why TS will be equal to NTB in MRA, but this is binary. So because N is 1, TS will be TB here. So that's why what is the Euclidean distance of BASK in terms of bit energy? Root EB, where EB is PS into TB. Okay. So similarly, what is the Euclidean distance for FSK? Root 2 PS into TB, because TS is TB. Or you can also say it as root over 2 EB. And next, what is the Euclidean distance of PSK? It is 2 root PS into TS, or else 2 root PS into TB, because TS is equal to TB. Or else you can also call it as 2 root EB. So it is root EB and this is root 2 EB, and our PSK is 2 root EB. So almost all you can see that Euclidean distance for BPSK is very high compared to the ASK and FSK. Okay, next, what is the bandwidth of ASK? 2 FB. And what is the bandwidth of FSK? 4 FB. I think you can see the spectrum of FSK. We have discussed in module 6. And similarly in BPSK, the bandwidth is 2 FB. And because here Euclidean distance is more, the probability of error will be less in PSK. That's why what we did, like there is a lot of research held in the case of BPSK by reducing the bandwidth. Because bandwidth of BPSK is 2 FB, and for QPSK, it will be 2 FB by 2. So it will be FP. Because what is the general expression for bandwidth of BPSK? 2 FB by N. Okay. In BPSK, N value is 1. So that's why 2 FB only. Next in QPSK, 2 FB by 2. So it will be FB. And in 8 array PSK, what is the value of bandwidth? 2 FB by 3. So you can see one thing here. As we move, or as you increase the value of N, or else you can say if you group more number of bits, if you group more number of bits per symbol, we can reduce the bandwidth. But that you can see by seeing the relation between bandwidth and the number of bits grouped per symbol. Bandwidth is 2 FB by N. Okay. Similarly in ASK, which parameter will vary? Amplitude parameter will vary. Amplitude of carrier will vary. So that's why noise accumulation is more in the case. In FSK and as well as PSK, the amplitude of the sinusoidal carrier is constant. Okay, and in BASK, the probability of error is high, because I told you the Euclidean distance is very less. Our probability of error will be high. And next, in the case of FSK, the probability of error is also high. It's very high because of having two carriers. Okay, so it is high, not that much high. It's in between ASK and PSK. In PSK, here you can say that because the Euclidean distance is very high and because of its constant amplitude, the probability of error is very less compared to ASK and FSK. Okay, and what about noise immunity? Here amplitude parameter will differ. Amplitude parameter will differ in ASK. That's why noise immunity is very less. And in FSK, somewhat increased. Okay, because its Euclidean distance is improved. And what about the noise immunity in PSK? It is very high. Immunity is very high, and because of its constant amplitude and high Euclidean distance. Okay, so this is all about the general comparison. And if you want to compare in various factors, you can also compare it using various factors like what are the kinds of detection techniques used and what kind of modulation. Here in ASK, you know how to generate ASK signal. By multiplying carrier with unipolar NRZ, you can get ASK. How can you get PSK? By multiplying bipolar NRZ with the carrier, you can get PSK. And here FSK signal can be obtained by using two carriers, I channel and Q channel. So like that, you can write the general expression and you can write the detection techniques. In both ASK and FSK, you studied coherent and non-coherent detections. In PSK, you studied the non-coherent version of PSK as differential PSK. Okay, so many factors are there. You can compare in all aspects, but we mentioned like a few key points. And here this is a generalized comparison. So here in ASK, FSK and PSK, what are the constant parameters? In ASK, frequency and phase of carrier remains constant. In FSK, amplitude and phase remains constant. And in PSK, the amplitude and frequency of carrier remains constant. Okay, and what about bandwidth? The bandwidth is 2 FB, so it is low. In FSK and FSK, it is high because already you studied 4 FB. In PSK also it is low, it is equal to 2 FP. You can still reduce in PSK by using MRA techniques. And what about noise? Noise is high in the case of ASK technique and it is low for FSK and PSK because noise immunity is high for PSK and FSK compared to ASK. And already I told you the probability of error for ASK is high. So that's why our noise SNR will be low. And SNR is good in both FSK and PSK. And what about data rate? Data rate is less for both ASK and FSK. And for PSK, you can group like more number of bits. There is a flexibility. Okay, you can construct MRA transmission techniques for both ASK and FSK, but the flexibility of phase change is more. That's why MRA PSK has a lot of advantages over MRA ASK and FSK. And the polarity of the input signal is unipolar for both ASK and FSK. But in the case of PSK, already I told you, it is bipolar. So it's polar signal. It's a bipolar format. Next, now here today I will discuss some of the problems. Sometimes these questions, this model you may get in GATE. Okay, for entering into like master's degree. Please observe the figure shown here. Now, any one of the student, please respond to my question. So, my question is, for the signal constellations shown in the following figure, tell me the type of the modulation. See, here you have 4 symbols, S1, S2, S3, S4. Which type of modulation it is? Tell me, observe the signal constellation diagram and tell me which kind of modulation it is. Any one of you. So here can you see constellation diagram here? You have 4 symbols here. And these 4 symbols are of constant amplitude. Here amplitude of S1, S2, S3, S4, all everything is constant. And please observe the carriers. Sin 2 pi n by t t, cos 2 pi n by t t. So if you observe the carriers, you can see that Fc is constant. That is carrier oscillator component is also constant. But you have in phase and quadrature phase. And what about the phase of S1, S2, S3, S4 with respect to x-axis? So based on that, we can say that it is which type of modulation?
QPSK.
Because why QPSK? Because the phase of S1, S2, S3, S4, everything is different. Okay, so phase parameter is differing here, but the amplitude of all the values is constant, and it is in general root PS into TS. Okay, this type of questions you will get in as objective questions. Okay, sometimes earlier days this is the gate question. Okay, like in 1999, like that, during that period. Not now, like past decade, these are the following gate questions. And one more thing is regarding our digital communications, you will get more number of gate questions only from chapter 2 and chapter 4. Because chapter 3 is just the extension of chapter 2, where you will solve only the probability of error for the corresponding keying techniques. Okay, so you will get more number of questions from chapter 2, because chapter 1 is like comparison of PCM and delta modulation. So once you know the noise power and SNR for both the techniques, that is like enough. Okay, based on constellation, you will get more questions. And calculation of bit rate and baud rate. Okay, so I think you can conclude that it is QPSK. Why QPSK? Because 4 symbols are there. 4 array PSK. So that is nothing but quadrature PSK. Okay. Next. So please observe this another question. Here you can see 4 waveforms. You can see 4 waveforms. Please observe the corresponding waveforms and tell me which first one is the output for which kind of keying technique. So I will call one of you. Please respond. C1 is on hold. What is extra duty for him? C2?
Yes, ma'am.
Okay, ma. Please listen to my question. Can you see 4 waveforms here?
Yes, ma'am.
Please tell me, these are the outputs for which kind of keying techniques? First one, please tell me.
ASK, ma'am.
Why ASK?
AC cos omega CT for input 1, ma'am.
Yes,
And,
for input 1, AC cos omega CT. And you have 0 magnitude for?
Input 0, ma'am.
Yes, very good. Next, second one is for?
FSK, ma'am.
Because you will have high frequency for data bit 1 and low frequency for data bit 0. Because AC cos 2 pi FHT for data bit 1. And for data 0, it is how much? For data 0, it is AC cos 2 pi FLT. Now please observe the third waveform and tell me it is the output for?
QPSK, ma'am.
Third one.
BPSK, ma'am.
BPSK or QPSK? When can you say it is BPSK and when can you say it is QPSK?
More number of phase changes unte QPSK.
More number, very good. More number of phase changes, you can, more ante enni undali?
4.
4 phase changes for the corresponding. So within a particular symbol, you will have even data and odd data. Okay. So like that, you will have two, like the combination of I phase and Q phase gives you the total change. So third one ఏంటంటారు ఇప్పుడు? Third one is the output for PSK. Why PSK? Can you tell me the general expression for PSK? Binary PSK. Ma C2. Can you tell me the general expression for PSK?
AC cos of omega CT for input 1, ma'am.
Okay, that's why you got same as carrier. Okay.
AC cos omega CT plus pi for 0, ma'am.
Okay, that is nothing but minus AC cos omega CT for data 0. Okay, like that you got the corresponding response. Okay, very good. And why the fourth one is for QPSK? In QPSK, you will have, it is a sum of output due to the I channel and output due to the Q channel. That's why the phase is not equal to either like sinusoidal or cosine. Here you have some different phase shift. Okay, it is a sum of I phase and Q phase, because in QPSK, if you observe, in QPSK, if you observe, you will have 4 phase changes as you said. And one more thing is, it is the sum of I phase and Q phase. Sum of, that is the sum of I channel will be SC of T, and sum of Q channel will be like S naught of T we defined. That is due to the odd sequence. Okay, okay, ma, thank you. Next question, please all of the students carefully observe this question. This type of model you will get like more based on this equation, you will get more number of questions. See here, the baud rate for the signal, here you are asking, you are asked to calculate the baud rate. What is baud rate? In general, the symbol rate is generally called as baud rate. Actually, every time we discuss that 2 bits are grouped per symbol, 3 bits are grouped per symbol, and a sequence possesses a more number of symbols, and each symbol consists of certain number of bits and cheptuna. Okay, that symbol rate is nothing but the baud rate. Symbol rate is nothing but the baud rate. Symbol rate or sample rate or element rate, or you can call it as in general baud rate. So Fs is nothing but the baud rate. Okay, so the baud rate for the signal having bit rate of 1 megabits per second being transmitted through QPSK using non-return to zero level digital encoding technique is dash. Please always remember that the baud rate is defined as the ratio of bit rate to that of number of bits present per symbol. Okay, here instead of symbol they called it as signal elements. So please observe the element there. The element may be sample or symbol or signal elements or whatever they have mentioned for the particular application. Here it is given signal elements per second. Signal elements per second. If you take it as symbols per second, okay, so you are going to calculate the baud rate in signal elements per second, or you can also call it as this as bauds. Okay, so here bit rate is given as 1 megabits per second, and in QPSK, what is the value of n? How many number of bits are grouped in QPSK? 2 bits. Because 2 bits, you will have 4 combinations of phase changes. So 4 symbols will be there. Okay, so in QPSK, you will have 2 bits are grouped. 2 bits are grouped. So that's why n will be 2 here. So baud rate is equals to bit rate divided by n. Here in QPSK, n is 2. Please substitute. So it will be 1 into 10 power 6 divided by 2. So it will be 5 lakh signal elements per second. 5 lakh signal elements per second. This is the calculation of baud rate when given bit rate. And some clue will be given to evaluate the value of, to know the value of n. For QPSK, you should know n value is 2. And you should know for 8 array PSK, m value is like n value is 3. Because 3 bits are grouped there. And in 16 array, you should know 4 bits are grouped. Okay, so n will be 4. Like that you should know. Then only you can solve this kind of problems. Now, please observe the next question. An analog signal carries 4 bits in each signal unit. Here, please observe Here the symbol, every time we call it as symbol. Here for the particular application, they called it as signal unit. Okay, 4 bits are grouped in signal unit. 4 bits are grouped in signal unit. So n will be 4. N will be 4. Now, if 1000 signal units are sent per second, find the baud rate. That is your question. See, please remember, here the answer is directly given in the question mentioned, because here he said 1000 signal units are sent per second. So here he did not mention that 1000 bits are transmitted per second. If that is given, bit rate will be given to you. Bit rate is given to you. But here he mentioned 1000 signal units are sent per second. So it means that baud rate is given to you directly, and you are asking to calculate the baud rate. So this is like an indirect question. So answer is given directly in the question itself. That you should know. Otherwise, what you will do? You will take 1000 divided by 4 something, or you will do. Okay, don't do like that. So this is like an indirect question where answer is directly mentioned in the question itself. Okay, this is an indirect way of confusing you. So answer will be directly given to you, but what you will do if you don't know clear information, you will do 1000 by 4 something you will do, and the answer will be given in multiple choice question. Like 1000 by 4, 250 will be given to you. Okay, 4000 will be given to you and 1000 will be given to you. What will you will do? You will put some 4000 or 250 something. But actually here answer is given in the question itself. So that's why you should carefully identify what is bit rate and what is baud rate and what is n. N is 4 bits are grouped in signal unit. So signal unit per second is nothing but baud rate. Okay, and bits per second is nothing but the bit rate. See, baud rate can be either symbol per second or bauds. In terms of bauds, you can directly calculate signal units per second or sample per second or signal elements. In the last question, they have mentioned like signal elements. So signal elements per second. Okay, alane symbol per second. So anyhow, they may mention you the corresponding element here. Here the element is signal unit. So 1000 signal units per second is nothing but baud rate. So directly baud rate is given to you. No need to calculate. Okay. Next question is, for the data given in the above question, find the bit rate in bits per second. Bit rate in bits per second. So if the following question is like this, then you can know that 1000 is not bit rate. Otherwise, you may get confused. So signal units per second is nothing but the baud rate. Now what is the next question? Find the bit rate in bits per second. Already you know the relation between bit rate and baud rate. Baud rate is bit rate by n. Baud rate is bit rate by n. Here n is 4. And our baud rate is given because you got already baud rate. So baud rate multiplied by n will be our bit rate. So that's why 4000 bits per second is our answer. Okay. So did you get this question carefully? So how can you calculate what is the relationship between bit rate and baud rate? Baud rate is bit rate divided by n. This you can observe directly from Ts is equal to NTB expression. Because Ts is nothing but the symbol duration. TB is bit duration. If n bits are grouped per symbol, you can obtain the symbol duration, because n into TB will be our symbol duration. And reciprocal of symbol duration is nothing but baud rate. And reciprocal of TB, that is bit duration, will be our bit rate. Bit rate is nothing but 1 by TB. Baud rate is nothing but 1 by TS. Baud rate is Fs, which is equal to 1 by Ts. Bit rate is FB, which is equal to 1 by TB. Okay. And what is the relation between bit rate and baud rate? baud rate is bit rate by n, or bit rate is baud rate into n, because TS is equal to NTB. Now, please all of you carefully observe the third question shown in the corresponding slide. The data rate of 8-array PSK is dash times that of BPSK. Here, please always remember that you should know what is data rate. Data rate is nothing but the signaling rate or information rate or transmission rate. It is defined as, it is represented with a capital letter R. Already I told you the expression. It is n into Fs. So data rate is n times that of Fs. Okay. So for a particular phase shift keying, Fs, for example, if it is constant, for the particular question shown here, the data rate of 8-array PSK is dash times that of BPSK. For 8-array, n will be 3 because 3 bits are grouped. So n into Fs will be 3Fs. And for BPSK, what is the data rate? It is only Fs. So 3Fs will be thrice to that of Fs. So that's why the data rate of 8-array PSK is thrice to that of BPSK. The data rate of 8-array PSK is dash times that of BPSK, because this is n is 3 and here in BPSK n is 1. So thrice. Similarly, what is the data? The data rate of 16-array PSK is dash times that of BPSK. Any one of you please answer to my question. The data rate of 16-array PSK is dash times that of BPSK. 4. Similarly, if data rate of 32-array PSK, it will be 5. For 64, it will be 6. Like that, based on the value of n, what is the expression used for this? R is equal to n into Fs, where R is signaling rate or data rate. Okay, like that you should solve this type of questions. And please observe the next question. So you should answer to my question now. A constellation diagram consists of equally spaced points on a circle 45 degrees apart. 45 degrees apart. If bit rate is given to you and you should calculate the baud rate. So to calculate baud rate, you should know the value of n first. How many bits are grouped? So what is a clue given to you? A constellation diagram consisting of equally spaced points on a circle 45 degrees apart. Now you should know what is the general expression for phase difference between two successive points in M-array PSK. What is the phase difference between two successive points in M-array PSK? Then you can know it is which kind of PSK. Any one of you please respond to my question. What is the general expression for phase difference between any two successive points in M-array PSK? Any one of you please respond. Almost all 51 students are there. Any one of you please respond, not to particular person. C9 is there? C9. Ma C9 unnara? D9? D9 is not there. E9? E9. Okay. So can you please tell me what is the phase difference expression in M-array PSK? Ma cheppandi. What is the phase difference between two successive points in M array PSK? You don't know that question? F9, F9. G9, G9, G9.
Madam,
Okay, can you please tell me what is the phase difference expression in M array PSK? చదవడం స్టార్ట్ చేయండి మిడ్ ఎగ్జామ్స్ like I think next week itself you will have mid exams. Okay, H0,
2 pi by m.
2 pi by
M.
m. Now please tell me which type of keying technique you will have a phase difference of 45 degrees for between two successive points.
8 array, ma'am.
Why?
Because m is equals to 8, then 2 pi by 8 equals to 5 by 4, ma'am. Phase difference is 5 by 4.
Okay, so phase difference is pi by 4 if it is 8 array. Now
Yes,
for QPSK, what is the phase difference between two successive points?
5 by 2, ma'am.
Pi by 2.
2.
Okay, what is the phase difference between two successive points in BPSK?
BPSK, ma'am. 5, ma'am.
Okay. Okay. So finally, you can conclude that it is 8 array PSK. So for 8 array PSK, what is the value of n?
3, ma'am.
N is 3. Okay. So baud rate is you should calculate the baud rate. So what is the
6,000 by 3,
relation
ma'am.
between
6,000 by 3, ma'am.
6,000
Bit
by
rate by n.
okay. So you can get it as 2,000. Okay, ma. Thank you. So like that you can calculate because it is pi by 4. So it is for 8 array PSK. So for 8 array PSK, n value will be 3. So you know that baud rate is bit rate divided by n. So bit rate is 6,000 divided by 3. So it will be 2,000 bauds. See, similarly, one more question you can see. For an 8 array PSK having a bandwidth of 5 kilohertz, the baud rate and the bit rate respectively are, see here the clue given to you is 8 array PSK. For 8 array PSK, you should know n value is 3 and bandwidth is 5 kilohertz. See, bandwidth is 5 kilohertz. You should know that for the PSK scheme, the baud rate is same as bandwidth. Okay, so in the case of PSK, the baud rate is, the value is same as that of the bandwidth because the bandwidth, so baud rate is Fs. Okay, it is almost all similar to the bandwidth in the case of any kind of PSK technique. Therefore, the baud rate will be 5,000 bauds. Okay, so for 8 array, you should know that n is 3. So bit rate will be 3 into 5,000 because bit rate is 3 n times that of baud rate. So it will be 15,000 bits per second. Okay. So anyhow, we can, if you go through internet, you can get more number of questions like this type of questions. You go through the internet. I will forward you the material. You can go through that. And one more thing is you will get more number of objective questions from chapter 2 itself. Okay, so please carefully read chapter 2 thoroughly. Okay, so then you can answer like good, you can be able to attempt. good, like more number of questions from DC as well as analog communication. Okay. Next, with this, we can conclude our chapter 2. And I think you can now, after completion of this chapter 2, you can be able to compare all the different kinds of digital modulation techniques, ASK, FSK, PSK, like its generation principle, detection principle, non-coherent and coherent version. I think you can solve. Okay. In the next class, we can continue with chapter 3. Today, I will just give you the syllabus of chapter 3. Okay, chapter 3 is data transmission. In this chapter, we'll just in this chapter 3, we'll just calculate the probability of error for the 4 techniques mentioned: ASK, PSK, FSK, and QPSK. For the 4 techniques, we should calculate the probability of error. Okay. And here we'll consider the best kind of receiver section. Okay, here we'll calculate the error performance for all the digital modulation and demodulation schemes. They're coming to our syllabus or the contents present in the corresponding 3rd unit. First, we'll go through the baseband signal receiver. This is the general receiver section. And here, using this receiver, we'll calculate the probability of error. First, we'll calculate the SNR, okay, output SNR for this baseband signal receiver and its probability of error. Then we'll consider the optimum filter and 2 kinds of filters we'll consider. See, optimum filter and matched filter. And coming to the coherent and non-coherent detection of FSK, already we completed this portion in module 6 of chapter 2, coherent reception and non-coherent detection of FSK. In this chapter, we will focus only on the probability of error calculations. Okay, so here actually the syllabus they mentioned in the data transmission, but we covered it in 2nd chapter. So you can go through our module 6 of chapter 2 so that you can see the mathematical analysis for coherent reception and non-coherent detection of FSK. And after calculation of this, we will go through the error probability calculations for ASK. See, every time whenever it is mentioned as ASK, it is nothing but the binary ASK, binary PSK, binary FSK, and QPSK. So total, we can split it into 7 modules. One is probability of error for baseband signal receiver. Second one is probability of error for optimum filter. Third one is probability of error using matched filter. 4, 5, 6, 7. So we can complete it in 1 class. That is probability of error for ASK, BPSK, BFSK, and QPSK. Or else here you can directly mention it as BASK. Okay. So these 4 derivations we can directly solve by using the expression obtained from the optimum filter response. Okay. So our first module will be baseband signal receiver and its probability of error. So here we'll calculate the probability of error for baseband signal receiver. So this is the general baseband signal receiver used for regular purposes. Okay. So this is also called as integrate and dump filter receiver. So here you will we'll integrate. So this is a receiver section. You can see this is a receiver section, and this is the input to the receiver. Sorry, input to the that is nothing but the transmitter X of t, and noise. Both are added in the channel, and the data is applied to the receiver section. Okay, you know that receiver consists of low pass filter. Right. Any kind of receiver consists of low pass filter followed by decision device. And here 2 switches are used. One is called as dump switch and other is sample switch. Okay, and here the IC is 741 IC. I think in linear ICs you can be able to know the importance of IC 741. So that is the best used operational amplifier, which can be used for varieties of applications. Here for this IC 741, and positive terminal is connected to ground. And for the inverted terminal itself, you are applying the input, and so input is applied via resistor, and feedback is given by the capacitor. That is, you are collecting the output from the capacitor. Okay, then you can call this IC741 with this external correction. Input resistance and output capacitance is called as low pass filter. Here for this IC741, non-inverting terminal is connected to ground. It's grounded directly. And for the inverting terminal, you have applied input via the resistance R, and feedback, you are taking the output via the capacitor. Okay. So once you take the output via the capacitor, you will get the low pass data. Okay, low component you will get, low frequency component. Okay, this is all about integrated dump receiver. We can start in the next session. Okay, we can start this chapter from next class itself, and later we'll calculate the derivations. We'll calculate the SNR. Okay, anyhow we can discuss it in the next class. So material, some material I posted in your group. You go through that. Okay. Any doubts? Or else we can wind up the session. Any doubts? From tomorrow onwards, we can start the third chapter.